Dear students, welcome to our class on JRF, SRF, NET 2022. Part C. In that Part C, we have a specialized subject, that is agriculture meteorology. In that, today we try to cover in this sixth class some bits exclusively with reference to remote sensing. Okay, why remote sensing? This is one of the components of agriculture meteorology. Here we completely dedicate today's sixth class for remote sensing bits. What is remote sensing by definition? Obtaining the information about an object without being in physical contact with the object, we call it as the remote sensing. I repeat once again, obtaining the information about an object without being in physical contact with the object, we call it as remote sensing. It's a wonderful science. It's an excellent science as far as agriculture meteorology applications are concerned. Extensively, we can use wonderful information of remote sensing. Usually, see, a satellite is there. Okay, that satellite is attached to a rocket. So the rocket goes up, leaving the satellite into the space. So there are different types of satellites: geostationary, geo-orbiting. So several those things in the form of bits we try to understand. Number one bit for today's class is that the radiation emitted from the Earth's surface is known as, you see, all the remote sensing revolves around the radiation, solar radiation, the energy coming from the sun. Now basically the reflected radiation, please note that this bit may come 100%. The reflected radiation is sensed by the remote sensing equipment. Remote sensing equipment senses the reflected radiation based on the characteristic features of the reflected radiation. So what is that object? What are the there are excellent uses that I had covered in the introductory agrometeorology and climate change, as also in micrometeorology. Okay, you please subscribe to my channel, Agrometeorology Farmers and there I had covered to the extent possible, the best way, the remote. Still I am going to cover. Now here, first bit is the radiation emitted from the Earth's surface is known as terrestrial radiation. Second bit is maximum amount of radiation for a given temperature is called maximum amount of radiation. Maximum amount of radiation for a given temperature is called black body radiation, maximum. Okay, now the fraction of the incident radiation that is absorbed by a surface is known as absorptivity. Now I am here, a glass is there. Okay, a pen is here. Okay, a scale is here. Okay, my watch is here. So now here every object in and around you goes on absorbing radiant energy, goes on emitting radiant energy. Absorptivity plus transmissivity plus reflectivity is unity. Absorptivity, reflectivity, transmissivity is equal to unity. So that's why. Now the bit is the fraction of the incident radiation that is absorbed by a surface is called absorptivity. Now next bit is the temperature of the sun. Bits like this are very important. Temperature of the sun, temperature of the earth. Please note. Why? Because in the assertion and reasoning, or list 1 and list 2. In the list 1, capital A, capital B, capital C, capital D are given. In list 2, Roman letter 1, Roman letter 2, Roman letter 3, Roman letter 4 are given. Now pick up the correct answer. Here the answers in mathematical 1, 2, 3, 4 are given. Okay, A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D are given in the answers. Now here what I would like to say is simple things. Like this. In most of the things which I am covering are the basics with regard to remote sensing. Now the basic bit is what is the temperature of the sun? 6,000 degrees Kelvin. What is the temperature of the earth? 300 degrees Kelvin. Now the body which absorbs all the radiant energy incident upon it is called black body. This is the answer. Which law states that the absorptivity of a body is equal to the emissivity for the same wavelength of radiation? A lambda is equal to E lambda. That is Kirchhoff's law. Once again for your academic interest, which law states that the absorptivity of a body, this body, okay, what? The absorptivity of this what is equal to emissivity at what condition is at the same wavelength of radiation, at the same length of wavelength. That is the Kirchhoff's law. Now, another question with reference to basic laws. Which law states that the maximum intensity of emission is inversely proportional to its absolute temperature? It is inversely proportional to absolute temperature. What is inversely proportional to absolute temperature? Okay, the maximum intensity of emission. I am emitting some radiation. My emission is inversely proportional to, okay, absolute temperature. So this is given by Wien's law. In the following bits I will give further application of Wien's law after a couple of minutes from now. So which law states that the quantity of heat capacity emitted by a black body is directly proportional to fourth power of its absolute temperature? So it is the Stefan-Boltzmann law. Several times I told. Once again, what the Stefan-Boltzmann law states? The law states that the quantity of heat energy emitted. I am releasing the heat energy. My watch is releasing. The white paper is releasing. The glasses are releasing. So the amount of heat energy emitted by, okay, for example, for a black body, let us not consider all these bodies. For a black body is directly proportional to the fourth power of its absolute temperature. Usually, any object we see, same principle we use. Stefan-Boltzmann law. For example, in the infrared thermometer also, we use the same thing. Now, the radiation from sun scattered by the air and dust molecules is known as the sky radiation. The scattered radiation in the atmosphere. Sun is there, atmosphere is there, troposphere, stratosphere, mesosphere, ionosphere, exosphere. When sun's rays are entering it, some dust particles, some air molecules, they scatter the radiation coming from the sun. That's what we call it as the sky radiation. What is direct radiation? Direct radiation on both the hemispheres. Okay, direct radiation means which is not scattered, which is not reflected, is direct radiation. What is incident radiation? The incident radiation is the total, scattered, reflected, diffused, direct, all these things we call it as the incident radiation on any object, based on which the solar constant is defined. What is solar constant? Solar constant is the amount of energy falling, that is the amount, whatever the amount of energy that is falling in a unit surface area, 1 square centimeter area, for example. So it is mean distance between the earth and the sun in 1 minute. So calories per centimeter square per minute. What is calories per centimeter square? Langley, 1 Langley per minute. So what is the solar constant value? It ranges between 1.94 to 2.0, 1.94 TO2, okay, from there to 2.0 Langley per minute or calories per centimeter per minute. Why I am telling all these things is that, see, the radiation from the sun scattered by the air and dust molecules is known as sky radiation. The answer is sky radiation. As I said, 1 calorie per centimeter square per minute is Langley per minute. Okay, the space tool used for detecting tropical cyclones. See, in Andhra Pradesh, for example, Machilipatnam, there is a radar. So, what is that? It is a space tool used for detecting the tropical cyclones. Radar is the tool which is used. The answer is radar. Radars are used for tracking the cyclone. It is a space tool. Which energy is recorded by remote sensing sensor? This is what I told 2 to 3 minutes back. Before I start the class, I told. These are all the bits related to remote sensing. Remote sensing, sensors, they record reflected energy, not anything else. Now, few more most important bits. Remote sensing systems which provide their own source of illumination are known as active sensors. They have their own known source of illumination. Active sensors. What are the passive sensors then? Sensors which measure the naturally available energy. Naturally available energy are passive sensors which provide their own source, active sources which measure the naturally available energy are passive sensors. What is a sensor? Obtaining the information about an object without being in physical contact. So, it is only reflected radiation that the remote sensing sensors measure. These which will come. That's why I am telling several times. Now, remote sensing in visible remote sensing, okay, in visible NIR and mid IR, okay, infrared, near infrared, mid infrared regions is known as optical remote sensing. What is optical remote sensing? Sensing visible part, near infrared, mid infrared. These three things together we call it as optical remote sensing. Another bit, remote sensing in emitted radiation range is known as thermal remote sensing. What is thermal remote sensing? By definition, remote sensing in emitted radiation range. Emitted radiation range is called thermal remote sensing. What is optical? Optical is visible, near infrared and far infrared. We see the solar spectrum, ultraviolet is there, light part is there, infrared is there. Now, visible, near infrared, middle infrared, optical remote sensing. What is thermal remote sensing? The remote sensing in emitted radiation range is known as thermal remote sensing. Now, another bit is remote sensing in higher wavelengths from 1 millimeter to 1 meter is known as microwave remote sensing. This is what we use for the moisture content in the soil, microwave. So, what is microwave? Microwave remote sensing. What is microwave remote sensing? 1 millimeter to 1 meter range we use in the remote sensing. So, once again, just let's go back some 20 seconds back. What is optical remote sensing? Optical remote sensing measures visible, near infrared, middle infrared. What is the thermal infrared? Thermal infrared measures emitted radiation range. What is microwave remote sensing? 1 millimeter to 1 meter. Another thing, of course, even though it's a very simple bit, but try to remember. Sometimes simple bits only you make a mistake. So what is it? 3.8 into 10 to the power of 8. We know it, the speed of the light in the air. 3 into 10 to the power of 8 meters per second, or 3 into 10 to the power of 5 kilometers per second. So these things you should remember. Even though it's a very, very small bit, please remember. Now, the two fields consisted by electromagnetic radiations are two fields, electrical and magnetic. Two fields are there in a electromagnetic spectrum. The peaks we call them as the amplitudes, as you know. Here, the spectral range for UV region is UV region we use, okay, as I said in the our solar spectrum, UV part is, ultraviolet part is there, visible range is there, and infrared range, infrared, near infrared, mid infrared, far infrared. Now, in that, okay, UV region is 0.3 to 0.38, lesser than 0.30, what we call it as ultraviolet radiation, which is harmful. They have gamma rays, X-rays, whatnot. 0.30 to 0.38 we consider as UV part with reference to remote sensing. Now, what is radio waves? Radio waves we consider more than 30 centimeters. What are the microwaves? Okay, 1 micron to 30 microns in the earlier bit I told, up to 1 meter also. Now, infrared we consider 0.7 to 100 microns infrared. Okay, we consider in the remote sensing 0.7, sometimes 0.76 onwards as well. I have given the reasons for what. 0.7 or 0.76, why we take in certain sensors of remote. I have covered in the theory. Please note. Now, see, the emissivity of a true black body is 1. A true black body absorbs and emits equal amount of energy. That's why the emissivity of a black body is 1. The emissivity of a white body is 0. What all is falling, it is reflected. So please note that the VIB, ZYOR, okay, what all absorbed, what all the is the same amount of energy that is given out. That's why we call the emissivity of a white body is 0. The last bit for today's class is the geostationary satellites are located at a height from the Earth. Geostationary satellites are approximately 36,000 kilometers height from the surface of the Earth. So these are the bits that I would like to share. We meet in the next classes. Thanking you very much for your very patient hearing.